Every advanced AI chip, every military supercomputer, every next-generation processor below 2 nanometers. They all depend on one machine, and that machine uses light at 13.5 nanometers. ASML's High-NA EUV lithography system is not just another fabrication tool. It is the physical choke point of modern computing power. Without it, semiconductor manufacturing does not move below 3 nanometers. AI scaling slows. Compute density plateaus. The performance curve flattens. This is not software dominance. This is optics. Extreme ultraviolet lithography works by projecting patterns onto silicon wafers using light with a wavelength of 13.5 nanometers. That wavelength is small enough to carve structures measured in single-digit nanometers, features smaller than biological cells. But High-NA changes the resolution ceiling. NA stands for numerical aperture. It measures how much light an optical system can gather and focus. Standard EUV tools operate around 0.33 NA. High-NA systems increase that to approximately 0.55. That increase dramatically tightens focus. Higher numerical aperture means smaller pattern features. Smaller features mean denser transistors. Denser transistors mean more processing power per square millimeter. But pushing NA to 0.55 forces a complete redesign of the machine. EUV light cannot pass through traditional glass lenses. It is absorbed instantly, so instead of lenses, the system uses multi-layer mirrors engineered to reflect 13.5 nanometer light with near-perfect efficiency. These mirrors must be smooth at the atomic scale. If surface variation exceeds a fraction of a nanometer, light scatters. If light scatters, pattern edges blur. If pattern edges blur, transistor geometry fails. At 2 nanometers, failure margins are microscopic. The entire exposure process takes place inside a vacuum chamber. EUV light is generated by firing high-energy lasers at microscopic droplets of molten tin. That interaction produces plasma, which emits the required 13.5 nanometer wavelength. Generating stable plasma requires enormous energy. High-NA systems demand massive electrical input to maintain laser intensity, plasma consistency, and optical alignment. As resolution tightens, system sensitivity increases. And then there is vibration. At this scale, vibration becomes catastrophic. A truck outside the facility, structural resonance inside the building, thermal expansion from adjacent equipment. Any disturbance can alter pattern accuracy, so the entire machine rests on advanced vibration isolation systems. Temperature control is extreme. Structural rigidity must be maintained within microscopic tolerances. High-NA also reduces depth of focus. As numerical aperture increases, the focus window narrows. Wafers must be positioned with greater precision. Even slight misalignment increases defect probability. There is a trade-off between resolution and throughput. Semiconductor fabrication plants depend on volume. If exposure time slows too much, production output drops. If it runs too aggressively, yield declines. High-NA improves pattern density but raises manufacturing complexity. And then comes scale. These machines are massive. They require segmented transport, controlled environments, and months of calibration. Only a limited number can be produced annually. Only a handful of fabrication plants can support installation. That concentration creates leverage. AI development demands more compute. More compute requires denser chips. Denser chips require high-NA EUV. And high-NA EUV requires atomic-scale optics inside high-power vacuum systems shielded from vibration. The bottleneck is not code. It is physics. You cannot software optimize beyond optical wavelength limits. You cannot bypass atomic mirror tolerances with better algorithms. You cannot scale infinitely when power, materials, and vibration constraints tighten at every node shrink. Light behaves according to fixed laws, and at 13.5 nanometers, those laws define the ceiling of global compute density. As semiconductor manufacturing pushes below 2 nanometers, every improvement becomes more difficult. Power consumption rises, defect sensitivity increases, manufacturing precision tightens. At some point, scaling will collide with fundamental optical and material constraints. When that moment arrives, the question will not be who writes the most advanced AI model. The question will be who controls the machines capable of shaping light with atomic precision. Because at the edge of computation, dominance is no longer digital, it is optical.